Take that as a yes. So I guess in that case, well, I guess thank you everyone for joining us this afternoon on this talk on the patterns and practices for building resilient service applications. But first, let me just define what I mean when I say resiliency. The dictionary definition of resilience is the capacity to recover quickly from difficulties or toughness, which in other words is not about preventing failures, but to be able to recover from them quickly. And as Werner once famously said, that everything fails all the time, and there's nothing we can really do about that. And all we can do is to build applications that can withstand different forms of failures and be able to recover from them quickly. For example, in a data center, hardware fails all the time. So to withstand those hardware failures, we learned that we need to run our application on the multiple servers so we can withstand those failures to individual servers that we're running in our data center. And since data centers themselves, or in AWS terms, availability zones, they can also go down for different reasons, such as when I think US East went down during a storm in the cloud at one point. So we also learned that, we need to run our application across multiple availability zones to get the extra redundancy in case when a data center goes down, or even maybe across multiple regions so that if a whole region goes down, our application can still be up and running. And since individual servers have a limited set of resources in terms of CPU, memory, and network bandwidth, the more user requests each service have to handle concurrently, the more resources we have to use on that server. And a common failure mode we see is that when there are too many requests, concurrent requests going to a particular server, and then we end up saturating the CPU, after which latency starts to spiral out of control. And another reason why we need to scale out our application across multiple servers so that it can handle more traffic from our users. And when we have a distributed environment where services often have to coordinate with other servers and other services and depend on each other, then when one of these services have some kind of failure, it can potentially impact and cascade through the entire system because other services are depending on that one service. So when it goes down, everything fails, and then you end up sending a 502 response back to your user, and that's going to impact the user experience, which of course is not going to make your customers happy because they have to experience interruptions when they're using your application. And then when you have a microservices environment with lots and lots and lots of microservices, it's quite a common problem that many of us have had to deal with over the last 10, 15 years. And my name is Yan-Cui, and as Martin mentioned, I've been working with AWS for over 10 years now. And since 2018, I've been also one of the serverless heroes. And the last couple of years, I've primarily worked with serverless components, including migrating a social network to run entirely on serverless. A couple of years ago, I think that was 2016, which you can read about on this link at the bottom of the screen. So nowadays, I spend half my time working with Lumigo as a developer advocate, and Lumigo itself is a troubleshooting platform for serverless applications that really makes it a lot easier for you to debug even more troubling problems in a complex serverless environment. And the other half of my time, I work as an independent consultant where I help companies go faster for less by adopting serverless technologies successfully. So back to how do you then go about building resilient serverless applications? I really like this diagram from Uri Fredrickson. I'm pretty sure I pronounced that wrong. But I really like this diagram because it highlights the four sort of broad areas that we should consider when we think about the resiliency in our architecture. And it's worth considering that the Lambda gives us a lot of resilience out of the box, not just because we have an isolated execution environment for each and every single request that comes in from a user, so that we don't end up using too much memory or CPU for one request that can potentially impact other concurrently executing requests. In this case, with Lambda, every single request gets its own execution environment. So if one of them fails, it has literally no effect on any other user requests that are happening at the same time. And when you build the APIs with API Gateway and Lambda, you also get multi-AZ out of the box. Both API Gateway and Lambda will deploy your application to 3 availability zones by default. And with both API Gateway and Lambda, they're also both pay per use. So you don't pay for additional resources when you don't need to use them. And when you do need to use them because there's a spike of traffic that's come in, then the system auto scales as well. And what's more, you don't need to run additional load balancer in front of API Gateway because you also get that load balancing out of the box. So when a HTTP request comes in from a user, it hits API Gateway, it's going to get routed to one of the 3 availability zones. And again, you don't have to configure and pay for the load balancer itself. And when you're building APIs using serverless components, you're most likely also going to be using something like DynamDB as well, which, by the way, is also multi-AZ out of the box. But you can also configure DynamDB as global tables so that you can turn your whole API into a multi-region active setup by putting Route33 in front of your whole API so that when a request comes in, you can get routed to one of the regions, and then every region will have its own API Gateway, Lambda, and DynamDB. But then DynamDB global tables is able to sync the data changes across all of your regions so that when user goes to a different region, they can still access their data. And so I guess it's suffice to say that we get a lot of resilience out of the box when we're using serverless technologies like API Gateway, Lambda, and DynamDB. But we also have to be, I guess, wary of some of the built-in throttling that that is inherent in all of these services, especially when sometimes they don't align perfectly. That also applies to timeout settings as well. So API Gateway has got a maximum integration timeout of 29 seconds, but Lambda function has got a maximum runtime of 15 minutes, which means you can potentially run into timeout situations even though your functions are still running, because after 29 seconds, API Gateway would have stopped listening. The same goes to when you are processing messages from SQS with Lambda, because SQS has got a default visibility timeout of 30 seconds. So if your functions are taking too long to process a message, because it's got a much longer timeout, potentially those messages can become available again when picked up by another function, by another instance of your function. So typically what you want to do is to set your visibility timeout to be 6 times the Lambda timeout itself, so that even after Lambda function has timed out, if you're not lucky, then you make sure that the message can be processed again, and you don't have to worry about the same message getting processed concurrently by 2 concurrent executions. And then a common pattern for making our APIs more resilient is, at least in cases where we need to do CPU intensive tasks or things that are long running, because we have that 29 seconds timeout on API Gateway, is to offload a task to a queue first. And then API Gateway can respond to the caller to say, 202, but it can respond quickly. And then we can run that long-running task in the background using Lambda by picking up the message from SQS. And then we have, say, up to 15 minutes to process those messages. In this case, API Gateway can really quickly respond to the caller and say, yep, no, we're doing it in the background, and please check again for response. Maybe start doing some polling from the client. In this case, it also allows us to have a better way to absorb any downstream problems. So if a Lambda function is talking to some legacy system and that legacy system is having an outage, and we're not able to process those messages, then we have the delta queue, which can then capture those failed events that we can't process right now, and we can later on maybe do some manual intervention to reprocess them when the downstream system comes back. We don't have to worry about having to do everything and then respond to the caller when the within 29 seconds that we get with API Gateway. So when you've got delta queue with SQS, that's great. You can capture any messages that you can't process. But a common problem here with DLQs is that, well, we still need some way to replay those DLQ messages, especially if, like we mentioned, the original failure was down to some downstream system that was having some temporary issues. So this is why I created the Lumigo CLI, which has a whole bunch of different useful tools, including tuning your Lambda functions, memory size, and so on. But one of the commands also allows you to replay messages from a SQS delta queue and then put them back into a either normal SQS queue or Kinesis stream or SNS topic as well to make that flow a lot easier for you. So this pattern we've just discussed is great for those kind of find and forget tasks where the caller doesn't need to do anything with the response we send them from API Gateway, and they just need to have some kind of acknowledgement that we got a message and that the message is the task is being processed. But what about in cases where the client is waiting for a response from us, from our API? So a related pattern to what we just discussed is called the decouple invocation, whereby I guess the main difference to what we saw just now is that after we respond from the API gateway, the initial API request, we are going to return location header so that the caller can then pull that location header to say, is my result ready? Is my result ready? And then in the background, we have a worker that's processing the message. And when it's done, it's going to save the data into, say, DB. And so when the user asks for and posts for his result the next time, he's going to actually get back the response for his task. So this allows us to run long-running tasks in the background without worrying about the 29-second timeout from API Gateway. So in this particular case, as a walkthrough example, a request will come in, an API function would queue up the task in the SQS, and then it's going to save some token in the DB table, and the result is no, to say that it's not yet ready, and we're going to return a 202 with a location header. In the background, we have a Lambda function that's processing those messages from SQS, and it's going to start working on them. And when the user is polling again, no, we still have a result as no, so we say it's not ready yet because the background function is still running. But once the background function is done, it's going to save the data into DB, and mark the result as the result into DB. And so the next time the user comes in and asks for his result and posts for his result, we're going to say, oh, it's done. So in this case, we can actually fetch it from DB and return a 200. So that way, the user is finally able to get his result. But there's one more thing. Notice that in this case, we have actually a distributed transaction here, where the API function needs to do two things. It needs to write a message to SQS, and then it also needs to save something into DB, at least the initial result, which means now if we want to do this the right way, we need to make sure that we have some kind of a fallback, so that if one of this one part of this transaction fails, we should really just roll back the entire thing. So how do we go about implementing distributed transactions in our application properly? Well, there's the Saga pattern. It's a pattern for managing failures in a transaction, where each of the actions you're doing in your transaction has equal and matching rollback action to so that in case when something goes wrong, you will roll back different parts of the transaction. And here's a talk from Katie McCaffrey if you want to learn more about the Saga patterns. And the example she used in her talk is if you want to go on a holiday, which I guess none of us are doing at the moment. You have to book your hotel, and then you book your flight, and then you book your car rental. So that's a distributed transaction there, where you are interacting with 3 different systems. And what we can do is we can use Lambda functions to model each step of the transaction. And then we can use each step as well as the rollback for each of the transaction, and then we can have the step functions, the state machine, to represent the Saga and to coordinate it so that suppose we want to go on holiday from London to Dublin. Then the happy path, we book the hotel, we book the flight, book the rental, everything was good, everything worked. We can just complete the transaction. But in case we book the hotel and as we try to book the hotel, something went wrong. So we have to roll back any sort of temporary state changes we've made, and then we have to run the cancel hotel rollback action, and then we fail the transaction. And equally, when we succeed when we're able to book the hotel, but then something went wrong when we try to book the flight, notice the arrow from book flight to cancel flight. So that is when we have a problem, and we caught the problem. Now we're executing the rollback step. And notice that there's like a self-recursion here that is to retry the cancellation step if there's any problems with the cancellation. And then is after canceling the flight, is going to then try to run the cancellation step for the hotel change, and then fail the whole transaction. So in many cases, we can also architect the distributed transactions out of the application in the first place, so that we don't need to use the more complex patterns like Saga patterns. And we can often do this by using DynamDB streams, whereby a Lambda function, instead of writing to SQL, so API Lambda function, instead of writing to SQS and DynamDB, if we just write a record to DynamDB and use the DynamDB stream to pick up to invoke another Lambda function, which would then take the information you got from DynamDB, and then you publish those tasks into SQS instead. So that way we don't have one function that have to do multiple things. Or better still, maybe we can even skip the whole sort of sidestep thing. We can also just do the work in this DynamDB stream function, depending on how long this task is going to take. In cases where that background task can take a long time, then maybe we still want to publish it into SQS so that we can have more concurrent executions working on those tasks. In the simple cases, maybe we can just do the work inside the DynamDB stream function as well. However, when it comes to DynamDB and the Kinesis streams, there's also this interesting sort of error handling behavior you gotta think about, where messages are retried until success, which can be very useful in some situations. For example, where you're dealing with downstream systems, if a downstream system is having an outage, then your message gets retried until success. So when the downstream system comes back, we just pick up from where we left off, and then we process them at the maximum amount of concurrency that is allowed based on the configuration of our Lambda function and the event source mapping. So that if we have, say, 10 shards in the Kinesis stream, and we have one concurrent batch per shard, then we're going to be processing the events with 10 concurrent Lambda executions at a time. So in that case, when something comes back, we should be processing data at a much faster rate than before. Another thing to keep in mind when it comes to DynamDB streams, at least, is that even though Kinesis streams gives you up to 7 days of data retention, default is 24, but you can raise that to up to 7 days. DynamDB streams only supports 24 hours of data retention. So it's possible. So if it's possible for outages to last for more than 24 hours, or maybe when something happens over the weekend, you got to make sure that someone is able to then deal with the problem quickly. Otherwise, if you come back on a Monday, then you may end up losing all the events that you couldn't reprocess during that outage. So you need to have good alerting in place to make sure that when something goes wrong, that someone is able to intervene and make sure that whatever problems that you're having is dealt with before the data gets expired from the DynamDB stream itself. So nowadays, the good news is that AWS released this new feature to how you to dealing with poison messages, but also dealing with messages that couldn't get processed after all these different retries, because now you can configure an on failure destination, basically a DLQ for working with Kinesis and the DynamDB streams from Lambda. Right. Another thing to keep in mind is that This whole retry until success behavior can also render you vulnerable to poison messages, so messages that you just somehow can't process at all. So again, luckily nowadays we got some additional configurations we can play around with by overriding the retry attempt, so that it's not retry until success or expiry anymore, but you can actually set a maximum number of times a message can get retried from a kinesis or DynamDB streams. And you can also say that when there's an error in a batch, you can say, you know what, we want to quickly find out which message in that batch is a problem. And so if you enable split batch on error, then when a batch is failing on the Lambda, it gets halved and a half again. And then after that, the retry attempt count started kicking. And after all the retry attempts, after all the retry attempts you configure, then those messages that still can't get captured, still can't be processed, they're going to get shipped to the on failure destination, and you're going to get a payload like this, maybe in your data queue, like in SQS. The one thing you got to really be careful here is that notice this payload. This payload tells you the shard ID and the sequence number. So it tells you where you can get the data from the kinesis stream, but not the actual payload itself. And since the data is only in the stream for 24 hours by default, up to 7 days if you pay for the extended retention, you have to be really quick in getting the actual data before they expired from the stream. Otherwise, again, you're looking at the potential cases for data loss. And then if you're using, say, SQS with Lambda, since the SQS is a sort of pole-based service, there's actually a bunch of pollers that's sitting between SQS and your Lambda function, which the Lambda team is running for you. And it's going to grab a batch of messages, call your Lambda function, and then when your function successfully completes, it's going to delete that batch of messages on your behalf. Where it gets interesting is what happens if your function errors. Then the pollers doesn't actually delete the messages from SQS, which means that the messages becomes available again after the visibility timeout. Or after a few, I guess, attempts, those messages are going to get shipped to the data queue for SQS. And then you can then retry those messages later on. But the key thing to remember here is that those messages are they fail as a batch. So with SQS, it's a batch event source, so you can get up to 10 events per request to your Lambda functions. But when they fail, all 10 of them is going to fail, even if there's only one message that's the problem. So to deal with this, partial failures, I wrote a blog post on some of the strategies you can use. Mainly, there are 3 different strategies. Option number 1 is you just set your batch size to 1, so you never have to deal with any partial failures at all. Or if that's not an issue, because that's not a solution, because that's going to impact your throughput, then you may say, you know what, we can make sure that our processing is idempotent. So even if we had a partial failure, 8 of the messages succeeded, but then the whole batch failed, so the successful messages got retried again, then that's okay, because our processing is idempotent. But sometimes that's a lot harder to actually implement in practice, especially when you're dealing with lots of different systems, and you might have to use the Saga patterns to deal with some of the more complex environments where you're dealing with distributed transactions. So my personal preference is to actually you pick up a batch of messages from SQS and then you process them in, say, parallel or one at a time, but you capture, you put a try catch around each message so that you process them, you find out which messages failed, and then at the end of all 10 messages, you check, okay, do I have any partial failures? If not, then I can just return successfully from the function, and then the poller is going to delete the messages for me. But if there are some partial failures, then what you can do is you can call the delete message API on the messages that were processed successfully to manually delete them from the queue, and then you store an error. That way, the poller doesn't delete the remaining messages, which are the ones that failed, and then the next time, you're not going to process the same successful messages again. And moving on to, I guess, another common problems in the microservices, whereby sometimes we're doing the right thing and have the opposite effect. Imagine we have a Lambda function that needs to call some other microservice, service A here, and any moment in time we have a number of concurrent executions running. They're all talking to this service. Now imagine if this service is having some problems, and some of those requests are going to fail or it's going to time out. And so to make our application more resilient to temporary issues like this, we probably end up implementing some retry logic into our function, so that with exponential backoff, so that in the normal situations, this is probably the right thing to do, because we're going to retry a few times with exponential backoff, and this is what the AWS SDK does already. Except in cases whereby when service A is already having some trouble, maybe it just can't handle the load, and we have all these retries with exponential backoff, and then as well as we have a fresh request from new concurrent executions that are handling new requests from API gateway, for example. And since the service is already struggling, it can't handle all this extra traffic, and more of the requests is going to fail, and more of them is going to get retried with exponential backoff. But in this case, they're still going to get retried anyway. And then so on and so forth, until the service eventually just gets overwhelmed by the amount of traffic it's handling, and it's just dead on its feet. And this, my friends, is what we call a retry storm, whereby a problem can sometimes be exacerbated by doing the right thing and then retrying failed requests from our application. And the solution here is to use a circuit breaker pattern, whereby you can still have those retries, you can still do those exponential backoff, but after a number of consecutive errors or timeouts, then you will trip the circuit, so that there's no more requests from your application going to the service, and any request will just fail, throw an exception if the circuit is already open. And you probably throw some specific circuit is open exception or something, so that your application can handle those cases differently, maybe by returning a cache response from a previous successful request, or maybe return some default response if possible, so that you don't cascade the failures up the call chain. In this case, you're going to give the failing service a chance to actually recover and hopefully return to normal working states. And after that, you're going to allow one request through every couple of minutes to see, okay, is the downstream system back online? If it is, then great. You can close the circuit and assume things are back to normal, and you start to do the normal request and then the retry with exponential backoff. If not, then you keep the circuit closed, and so you keep the circuit open until such time that you get the successful request through to the downstream system. Now, a common question that comes up when you're implementing circuit breakers in microservices is, in serverless applications, is where do you put the state of your circuit? Because the concurrent executions themselves, they don't share any state. There's probably, broadly speaking, two different ways to do this. We can either let the concurrent executions themselves to keep its own state in memory, which I think is a lot simpler and have no external dependencies and doesn't need actual permissions to store the state. But the downside is that it is going to allow more traffic through to the backend system, especially when you've got new concurrent executions that's springing up because of more traffic coming through. And Lambda creates more workers in response. Or we can put the state of the circuit into something like a DB table, which basically the pros and cons have switched now, whereby you've got additional dependencies, but it does architecturally, but then it does help you reduce the number of requests that you end up sending to the downstream system.